Hi, my name is Minkyeong, and I'm excited to be talking about our paper KDA, Automated Data Generation Pipeline for Detoxifying Implicitly Offensive Language in Korean. We propose a fully automated pipeline that generates neutral toxic pair dataset. Especially, we focus on trends-aligned implicit toxicity with strong contextual consistency. KDA proposed a scalable, additive solution for modern language detoxification. Toxic language is becoming more common as the online communities grow. We focus on implicit offensiveness, cases that are subtle and harder to detect. When we look at the Korean online communities, we found that a large portion of harmful content was not explicit. It rather relied on ironic coded language or a tone to express toxicity. We also discovered that these implicit toxic statements fall into three main types. The first matches existing definitions, sentences like indirect insult or subtle stereotypes, but this only made up a small slice of the data. We see a bigger trend emerging in two types. First, community-specific slang. Expressions that only sound toxic if you're familiar with the group or the content. And second, various slurs. Modifications of offensive words to avoid moderation, like character tweaks. What's important is that neither of these may appear toxic without understanding of content or culture, making harder to detect using machines. So what was the challenge for building this kind of dataset? Let's break it down in three common types. First, the need for human labeling. Lots of previous work rely on human annotators to decide whether the sentences are toxic or how to paraphrase them. But this is not the cost-effective way and sometimes suffer from bias or low agreement within annotators. Second, poor quality of machine-generated dataset. This approach uses large language models to generate toxic contents, but the results often lack up the toxicity or deviate from the original meaning. And since these models cannot be updated in real time, they quickly become outdated. Third, translate dataset. Many existing datasets are in English, so people choose to translate this to other languages for building dataset. But this kind of translation often misses the nuance or cultural context. This limitation pointed us in a clear direction. We need a new pipeline which is scalable, culturally grounded, and adaptable to evolving language. So what exactly are our goals? We wanted to build a high-quality pair dataset that first capture evolving trends-aligned expressions found in the real communities. Second, focus on implicit toxicity for high-context language. And finally, ensure the toxic versions still share the similar content with the original neutral one. These three pivots are further crucial for training detoxification models. To achieve this, we propose the KDA pipeline. It has two main stages, retrieving real-world slangs and filtering them for high-quality dataset. This entire pipeline is fully automated without any human annotation. The first step is to retrieve real-world slang from online communities. First, we use AskBird to embed community comments and retrieve them that matches a given neutral sentence. This gives our LLM rich context, grounding it in how people actually speak online. And then, the model will write the sentence using the retrieved expressions. To make sure we get a good mix of relevant and diverse outputs, we use multiple retrieval depths from 0 to 9. Which depth works best often depends on the neutral sentence and the kind of embedded expressions. By generating output of each depth, we can get a wider range of responses from the model. We know that LLM outputs can be unstable. Some are the question answer, or some go off topic, or others just paraphrase. So we need a way to filter them out. We designed a two-stage filtering process, using LLM itself to evaluate the outputs. The first filter checks for pair consistency. If the toxic version changes the meaning a lot or adds unrelated content, it's gonna be discarded. The second filter checks for implicit offensiveness. Only those that pass both filters make it into our final dataset. Here's what it looks like in practice. We generate multiple responses with the different retrieval depths, and then filter them through both steps. This gives us the toxic neutral pairs that are contextually consistent, implicit offensiveness, and truly reflect real-world languages, all without any human annotation. We also evaluate the dataset using 5 metrics. First, overall offensiveness for general toxicity. Second, implicit offensiveness for subtle toxicity. Third, consistency for content preserved. Fourth, velocity for natural sentences. These 4 use GEval, a GPT-4 based evaluation framework. Lastly, we use Google's Perspective API to measure how harmful the content feels to real readers. All evaluation metrics follow the evaluation from previous work, except the implicit offensiveness that we define in this paper. So how did we perform? We compare KDA to existing dataset. KDA achieved the highest scores in implicit offensiveness and pair consistency. That means our sentences are both meaningfully toxic and faithfully grounded in the original neutral sentence. We also ran a human evaluation between KDA and KOMG since both are machine generated. While KOMG shows slightly better pair consistency, it has lower agreement within annotators. In contrast, our dataset has both high consistency and strong interleader agreement. To test generalizability, we apply KDA in 2 new settings. First, we apply it in English. The same pipeline successfully worked without any modification. Second, we set up the GPT-4 for open source models like Trillion 7 billion and Gemma 9 billion. Surprisingly, they still perform competitively, showing our pipeline is not tied to any one model. And this opened the door for multilingual dataset and fully reproducible pipelines. And of course, we test the real-world impact. We trained the detoxification model using KDA, KOMG, and CAT. Models trained on KDA consistently produce less offensive, more fluent, and more faithful neutralizations. This demonstrates that the quality and structure of our data lead to more reliable and accurate detoxification. And in human evaluation, outputs from KDA-trained models are preferred more often. Although our results show that KDA has a potential to generalize across languages and models, we plan to expand it in 2 directions. We will optimize the pipeline for other languages with a deeper understanding of each culture's context. And then we will explore ways to reduce the cost of large language models. Thank you for listening to our presentation. For more information like codes or dataset, please visit our project page in the slides.